Hello, good morning, and welcome to today's webinar. Uh, Talk today about an important subject, eddy current breaking. Of course, many of you know that it's becoming more important due to the surge in vehicle hybrid and electric vehicles. Um, can you hear me? Okay. Okay. Thank you. Okay. So our agenda is as follows. I'll talk about the design issues and the problems that have to be solved for eddy current breaking and explain a little bit the principle of eddy current breaking. Okay. Then we will show some results, simulation obtained by EMS, EMWorks solution. Then we go to a live demo of the software. All right, so eddy current breaking in principle is a very simple idea. You have a disk. This is a breaking disk. And what happens is when there is an applied, when the disk rotates in a magnetic field, whether the magnetic field or magnetic flux or magnetic field is applied through magnets, like in this case, what we call passive, or coils instead of the permanent magnets, you could have also coils, or both, what we call hybrid braking system, is more advanced system. So as the disk rotates inside the magnetic field, there is eddy current produced in the disk, and of course it's a conductor, whether it could be aluminum, copper, or steel. Okay, and based on Faraday's law, there is a current, what we call eddy current, is induced due to the motion of the disk in a magnetic field. If this rotation is counterclockwise, the current, eddy current, will be clockwise. It's going to oppose the motion that's causing it. And so the idea is to produce enough eddy current, opposite eddy current to the motion, so this disk stops. That's eddy current breaking system. So the main quantity that has to be optimized is the torque. Okay, so before even talking about how long it takes for it to stop and all of that, we have to design the disk and the magnets and all of that material and excitations and speed and all of that. So the torque depends on the speed of the disk, the gap, air gaps, what type of magnet, what type of material, what type of number of poles, excitations, and all of that stuff. So that is the crack of the matter, is to properly design produce proper torque. Then you talk about the acceleration torque. Okay, fine, you have now the necessary torque for stop. Stop, how long is going to take? Is it 1/10 of a second? Because once you brake, you want to stop almost right away, right? So that's also a design issue that has to be optimized. Now, a side effect of the This idea, which is an excellent idea, is the power, dissipated power, because the disk has to be a conductor. Okay. We know from Ohm's law that if you have a conductor and you have current inside the conductor, there are losses, conductor losses. Of course, if the disk is made of steel, you can have also uh, core losses. Okay? That's another design issue that, of course, steel is stronger mechanically, but then you could also have issues related to core losses. The losses produce heat, and the heat can cause thermal stress and deformation. So in the design process, you have to worry also about this issue of heat and deformation, structural deformation. As a matter of fact, if it heats up too much, this can actually break altogether. So these are the design issues that one needs to worry about. Okay, let's go straight to some of the examples. So this example here is called an axial permanent magnet braking system. Okay, this one configuration is the magnetization in all the magnets, the same direction, one direction magnets. Okay, and in this case, okay, as you can see here, you're going to need a back iron from top and bottom in order to close the magnetic circuit. Okay, so if so one rule of thumb here is if you want the permanent magnet aligned, have the same direction, you must have what we call back iron. Okay. These results are obtained using EMS. So as you can see here, this is the magnetic flux density. Okay, um, in the entire braking system. Okay, this is a fringe plot. These are the vector plots. Okay, and as you can see, this is a disk. Of course, underneath the magnets, the current, the magnetic flux is maximum. Okay, but as you can see using the vector plot, are all pointing down. So because all the magnets are oriented uh, in the vertical, they're vertically in the negative z direction in this case. You can these are also results using EMS. So the can density or the eddy current, okay, and this eddy current again is caused not by the variation of the excitation, because you can have eddy current due to sinusoidal current, or if you have a time varying excitation current or voltage, you're going to have eddy current. But in this case, actually, it's nothing is varying. Only variation is the motion. So all the eddy current, as you can see here, you see is significant actually, is due to motion. So you can look at the fringe plot, and obviously you have hot spots under the permanent magnets. Okay, uh, this is a vector plot of the same quantity, and this is what we call streamline. These are all using EMS. Notice that the maximum is 1.6 to the power 7 amps per meter squared. All right, let's look at these results. And this is again, all other results, by the way, they're all EMOX solution. Okay. One set of results, you want to look at torque as a function of speed of the disk. Here, just comparing to some published data, references, experimental and reference simulation. So as you can see, the higher is the speed, the more torque you can generate. Okay? On the right side, the dissipated power is also proportional to the speed of the disk. So what's the conclusion here? Well, there is a trade-off between torque and dissipated power. This is desired. You want to produce more torque to stop faster, but this is undesired because, as we said earlier, dissipated power means heat. Heat means deformation. So this is one of the challenges that the designer has to take into consideration, and the tool like EMS can help you understand, relate, So somewhere you have to find a compromise between the torque, the dissipated power. You see how much, what kind of material you have, on the disk, how much it tolerates, how much heat. And as we're going to see later on, some of the system actually they have a cooling. Some of the braking systems, the newer one, to get around this issue of heat, they have a cooling system using some fluids or oil to cool down the disk. And this is one of the major issues that one has to worry about. Okay. This is another configuration. This is called alternating magnets. Um, in this case, as you can see, uh, in one magnet, the magnetization points up. Next to it, it points down. All right. Now, the advantage of this configuration is you don't need what we call back iron. Why? Because the magnetic circuit is closed because it goes from one magnet, it goes through the disk and then through the other magnet. And so you're going to have, like as you see here in this magnetic flux density, how the magnetic circuit closes actually. So you don't need back iron. And of course, there are advantage and disadvantage to the back iron, right? Uh, because if you have back iron, you have your brake is sturdier, so it's heavier, but it is stronger. So these are some of the issues that one has to worry about. Again, these are the results obtained by EMS. Okay. Um, Notice the maximum current density obtained in this configuration is 3.12 10 to the power 7. Comparing to the previous configuration, you have a higher current density. Higher current density means larger torque, but again means more temperature, more heat. Okay. So this is the streamline, and this is just an animation of the eddy current in the disk. This is some other plot. So this is the magnetic field, the blue, and the orange purple is the actually the current. So I'm just taking a circle, a few points along an arc on the disk and see how the magnetic flux density varies as a function of position, and it's somehow periodic. Why it's periodic? Because these peaks are right underneath the magnets. So of course, the magnetic flux density and the current density, the eddy current density, so to speak, are higher underneath the magnet. Okay, let's look at this now. So as we saw earlier, okay, that the torque and power dissipated, both of them, the are proportional to the speed of the disk, which means the higher is the speed, the faster is the disk, the higher is the torque, and the higher is the power dissipation. And we said, as we said earlier, there is a trade-off uh, to be considered, to be designed around. Okay. But I'm showing you here in this particular case, when you have alternating magnets, you achieve higher torque. Unfortunately, again, you have more power dissipated. Okay. It's one of the observations is the effect of the magnetization direction. And again, uh, these are just some results, just to show sample results that you can obtain using EMS. All right. Now, this plot shows the effect of the back iron. Okay. So if you have a back iron, okay, this one, the red, you achieve higher torque. But again, back iron, of course, is more expensive, right? So you get more torque, but then you have to, it's heavier, and you have to spend more money to uh, buy the iron. So this plot shows you the effect of the back iron. So you get higher torque, definitely, as a function of time you see here. Okay. This one is the effect of the type of magnets. Okay. The blue one is the neodymium iron boron. Okay. You get higher torque. And then ceramic magnets. No, actually the cobalt magnets are next, and then the ceramic. And of course, there's a trade-off here. There is a cost. Okay, the iron boron are much more expensive, and they're heavier. Okay, uh, so there's a trade-off that has to be considered uh, when choosing the type of permanent magnets as well. Okay, let's look at the deceleration. Okay, this plot, this is what you eventually want to look at, right? The ultimate plot is these two plots, because that's what shows you the actual deceleration torque, or the braking. So depending on the initial velocity, okay, how much time does it take? Okay, so depending on the initial velocity, you can see the variation of the torque, and when it comes to a halt or stop. So um, it's for this particular design, I can think we have to basically zoom more here to see, but the initial velocity also has some effect on the deceleration or the stopping time. So this just showing the speed. The speed, of course, it has to go to zero when the torque reaches zero. And once zero, then we said, oh, it brakes, it stops. Your car stops. Okay, so for this design, it doesn't make a lot of difference, but you can look, say at uh, 10 millisecond, what is the speed, and this is also important to know the design, at each time step, how long, the speed at as a function of time. And again, it's going to depend on the speed, the initial velocity, at what speed you are driving your car. Okay, when you brake. Okay. Okay, just give me a second. I have to close this door. Okay. So this is your final product, right? This is your final product. So if you are making a current braking system and you want to sell this, you're gonna to a car manufacturer. So these type of ultimate results that you want to show, okay? How long does it take? If you are driving at this speed or that speed, one, the torque is going to go to zero, right? And these two, of course, are related. When the torque goes to zero, the velocity, the speed is zero. Okay. Let me show you some other systems. Okay. Uh, this is another eddy current braking system, active. Active because you have a coil right here, and the disk is rotating. As we observed earlier, that uh, the actually you're going to see it more when we do the actual live demo. Torque uh, keeps increasing as a function of speed, but at one point it reaches a maximum and goes down. So if you are thinking that the more speed, the higher the speed, yeah, we showed you earlier the speed, it keeps going down. But if you really keep increasing the torque, at one point it's going to start going down. Okay, and this one shows the torque as a function of applied current because you have a current in the coil. This plot shows you the effect of the number of poles. So these are 2 poles, 4 poles. You can have more poles. And as you can expect, the torque is really linearly dependent on the number of poles. The more poles you have, the more torque you can produce. What else? This one, just a quick plot here of some results for the hybrid eddy current braking system, okay, where you have both coil and permanent magnets. Okay, this is a disk. Okay, uh, it shows you the eddy current and the disk. This is fringe vector and streamline. For this uh, figure, it shows you the effect of adding permanent magnets. So you have coils, but you can see the effect of the permanent magnets. So it, when you have permanent magnets, okay, have more losses, but unfortunately the color are mixed up here because this one blue and this one orange. But for this plot, you know, the engineer helping me, he messed up the colors because you're supposed to have same color, but I apologize for that. So in this figure, the blue is with permanent magnets. So we have higher torque. And again, same observation. Higher torque means higher losses. Okay. This one shows you the deceleration torque and the eventual speed uh, with and without the permanent magnet. In this case, he did it correctly. So the orange are with permanent magnet, the blue without permanent magnets. Okay. So with the permanent magnets, you can actually stop much earlier because you're going to produce higher torque and it is going to go to zero much earlier. And you can see it in this figure clearly here. You can see the one with permanent magnets. Okay, it stops much faster than without permanent magnets. So again, it's a trade-off, right? Uh, the permanent magnet uh, are more expensive. Your whole brake brake system is gonna become uh, heavier. Okay, and of course, if you're gonna uh, so you so this is one of the issues again uh, that you can consider. Okay, is the effect of the permanent magnets. Okay, now let me show you another example of what we call double-sided ventilated disc. Okay, in this case, as we've been said earlier, that the heat is one major challenge, okay, in the eddy current braking system. Okay, and if you wanna have more torque, that whether by adding permanent magnets or using different materials or uh, you can't escape the heat. So a lot of this system, they have a cooling. So underneath the disk, okay, there is a back iron and there are slots where fluid, actually oil, can circulate to cool down the disk. And this more modern, more recent eddy current braking. And by the way, the eddy current braking, you can have it also. It's very popular in trains. It's not only in cars, even in larger vehicles, trucks, buses, trucks. Uh, there are many technologies vehicle nowadays use the eddy current braking system. Okay, and showing you again the current density. These are some plots of temperature because uh, as I'm going to show you later on in the live demo, the coupling uh, between magnetic and thermal. So this one showing you shows the temperature distribution. And again, I mean, you can say CE84C may be okay for certain material, it may be too much. So this is one of the design issues that you have to worry about. Okay. All right. So much for the PowerPoint presentation. Let me close it. I'm not going to save and go straight to the software itself. So this is what I just showed you, but without the cooling system to make it easier to manage. Okay. So EMS, as you know, is integrated in SolidWorks. So uh, SolidWorks is one of the most popular CAD packages. So it's easy to use and it's parametric. You can change and you can. It's a very powerful CAD system. So we are lucky that our software has been part of SolidWorks CAD for many years right now. It's almost 15 years. And in addition to coupling to the CAD, we also use SolidWorks Motion. This is very important when you're doing motion, okay, because SolidWorks Motion, like in this case, you can have many different studies and you can couple to different SolidWorks Motion. And you know that SolidWorks Motion use add-ons, the very popular motion product for MSC, I think. Um, it's very powerful because you can do a lot of it because it's meant to for mechanical systems, and we only use a very small part of the SolidWorks Motion. Okay, because it is integrated in SolidWorks, then there is no need for import, export, data, heal data, fixed data, clean data, geometry, none of that. We are right inside the CAD. So this is a big plus. All right. So let's look at EMS. Some of these, okay. Let's see why it's taking a minute. Okay, here we go. So here we go. Now I have several studies. I'm going to show you some of the results. By the way, just quickly, uh, the way you couple to SolidWorks motion is by choosing motion coupling. That's it, as easy as that. You don't need anything more than that. And then you decide to which motion study you want to couple. Yeah. And in this case, you have many different studies. Okay, that's all it takes. And then the rest of it is applying material. It's just we have tons of videos on YouTube, our YouTube channel, how to apply material, how to apply coil excitations, and all of that. It's all explained. Okay, in this case, you have the of course the coils are copper, the ferromagnetic poles are steel and nonlinear steel in this case. So this is nonlinear. Okay, it is nonlinear eddy current motion coupled to SolidWorks motion. Okay, just one thing that I wanted to bring your attention to is this issue of turning on and off eddy currents. In the disks, our the current is on. You see the symbol here. In the poles, even though they are conductors, it's off. We are not interested in the eddy current, at least in this study, in the magnetic poles, ferromagnetic poles. We are mostly interested in the disks, and the disk here happened to be chosen to be aluminum. Okay, you're going to make sure. And the whole idea, of course, you cannot turn the eddy current off in the aluminum for this case. Otherwise, nothing is going to break, right? But the whole idea is to use eddy current to stop the disk. So you must make sure that the eddy current option is on. Okay, so let's look at first set of the results. So I'm going to hold my control key down, choose these four studies, and these four studies, okay, uh, they're showing you some of the results I showed in the PowerPoint presentation. Okay, so I'm going to do a right click, compare results, transient magnetic. Okay, I'm going to bring to this window here. Okay, so the results table has all of your mechanical, like the force and torque, and circuit or electrical parameter. So as you can see, I have the force, torque, the current in the coil, the inductance. Okay, I have only two coils here. The flux linkage, the induced voltage or the back EMF in the coil, losses, solid loss. Okay, uh, as you can see, the solid loss only in the disks. Okay, because the ferromagnetic poles, even though they are conductor, but they don't have any current. Uh, and more winding loss in the coils, resistance, energy, so on and so forth. So let's look, as we said earlier, the torque is really what interests us most. So we say, click on TZ, and you say add, then you know plot. All right, so let's look at this. So as we saw in the PowerPoint presentation, 100 RPM is the blue. Then the next to it is 500 RPM. So the blue we have about 10 Newton meter. Red is almost 27. Okay, but look at this. We said earlier. We said the torque you have more torque. Okay, uh, at higher speed. But see, that's only part of the story, okay? Because when you keep increasing the torque, okay, like in this case, 1,000, like 2,000, okay, 1,000 RPM. Yes, when you start, yes, you have more torque. The the green and the orange. Yes, you have more torque, okay? when the disk starts spinning. But, but as it keeps spinning, it actually converges to a lower torque. Okay. And again, this is because of eddy current itself. This is a phenomenon due to the eddy current. So the speed, yeah, we said earlier that yes, you get a more torque, but only to a certain level. So in this case, 500 RPM. So eventually it produces more torque than 1000 RPM or 2000 RPM. Okay, so this is a very interesting uh, observation that you can see, okay, given by this plot. That's one. Any of these quantities actually are plottable as a function of. Let me see if I have a if I could plot the solid loss in the disks. Okay, okay, because this is okay. Um, so the blue is my 100 RPM, 500 RPM, 1000 RPM, 2000 RPM. Okay, so what can we say about this? Well, um, unfortunately, um, the more speed, the higher is the solid loss. The higher the solid loss, the more temperature, the hotter, and again, possibility of deformation and breaking. So, uh, so it is proportional. Unlike the torque, okay, uh, the loss, okay, and actually that's one of the reasons, actually the as it starts heating up and you get a lot more eddy current, then the torque is going to reach a maximum and then starts going down. Okay, so so any of these data, any of these results actually are plottable as a function of time. You can also plot, these are the sword motion results, the angular velocity, the angular acceleration. You can plot them. Okay. Of course, this you can export this data, print it, and so on and so forth. So these are one first set of results. Let me show you another set of results. This is the effect of the initial speed. So, so I'm going to compare my results, and I'm going to jump straight to the torque because that's what is the most important. Here we go. So in the blue is the initial speed of 1000 RPM. Red is 2000 RPM. Okay, and as you can see, okay, um, the time it takes, okay, uh, to reach zero speed or zero torque, as you can expect, it takes longer. If you are driving at a higher speed, okay, definitely, uh, indeed, it's going to take you more time to come to a halt or to a stop. So this is also uh, the effect of the initial velocity or initial speed of the disk. Okay. I can also show you some of the results. Uh, okay, last study. Okay, I'm going to show properties. This one, we requested thermal coupling and motion coupling. And again, as I said earlier, motion coupling, you can choose which motion study that you want to couple to. And in terms of thermal coupling, you can do steady state thermal or transient thermal. And this one is the ambient temperature. Okay. All right. As you can see, interesting thing about EMS is all integrated. The thermal solver is not a separate program. You don't need to export your electromagnetic or loss and feed it to a thermal program and different windows, different results, different interface. No, we provide an integrated interface where you can specify. So when we have coupling, you're going to have, see, notice that we have electromagnetic input and thermal input. So this is when you specify this electromagnetic input, in this case, just the coils and the force calculated Lorentz force on the disks. Okay, thermal input is a full-fledged thermal solver. You can specify the temperature, the convection, heat flux, volume heat, radiation, all of them. But in this particular case, we just have convection. The convection is coming from the surrounding air. Okay. Um, the results, again, results state the magnetic flux density. Okay. Uh, I can uh, animate magnetic flux density. Okay. You see. Okay. The current density can also animate my current density in the disks. Okay. Uh, So these are the magnetic results. So again, previous videos, we've extensively covered all of these results, how to plot, how to do, because you can do fringe plot, vector, streamline plot, 2D plot, uh, all of them, the magnetic field, the applied current density, the current density or the eddy current, the force density, the flux, the loss density, all of them, what we call electromagnetic results. Now, another second folder is actually the thermal results, where you can plot the temperature. Okay, let me see. Okay, this is temperature in the disk. The first one just showed me the temperature and the magnetic pole. Okay, and this showing you the temperature in the disk. It reaches 180 C. And again, it depends on the material, depends on the design specs, whether this is acceptable or not. Of course, you can do temperature gradient, heat flux, so on and so forth. So to conclude, this product, this EMS has the coupling to sword of the cat. It has a coupling to sword of motion. So you can do really the most complicated motion you can do, as many of you know, this is the sword of motion. So you can do a very sophisticated motion. Okay. Uh, and also the integrated coupling to thermal and actually even to structural, by the way. Okay. Um, Last but not least, when you're eventually done, you want to produce a report, okay? And then you can uh, customize your report. I put my name, okay? Company name, date. You can produce a Microsoft Word or an HTML. Okay? So now the report, it actually it it's a it documents your work. So you don't need to write down your input or output or results or worry about that. So of course, it's HTML file ready to be shared with others on the internet or otherwise. So it has the file name, the model view, the material, each material, okay? It has the coil information, the force torque, all the results that we spoke, that we showed earlier, okay? Oh, all right. So that's basically it. Um, the my presentation today. Okay. So it's just uh, to conclude. This EMS is a powerful tool if you want to optimize, design uh, eddy current braking system. Okay, so with that, I'd like to thank you very much, and I'm going to stop sharing my screen, and the floor is open for your questions. And please type your question on the chat region on the right side. Okay, all right. So how is the study coupled with motion study? What is getting from the motion study? Okay, so what it gets from the motion study is basically the Newton equations, the dynamic. So so what we feed to the SolidWorks motion, we give it the torque. Okay, so we give it the torque at this time at this time position, and then we say, okay, now based on this torque, and of course the material, okay, because force is equal mass times acceleration, right? Because material matters, right? I didn't show you, but in the material you have to specify the proper material. Okay, uh, then the SolidWorks motion, it solves Newton's second equation of motion, okay, and tells us, okay, based on this torque and this mass, here is the acceleration, and here is the next position. So based on that, that's going to give you the next position. And that next position, you say, okay, then we goes back to EMS. It is an interactive process between EMS and the SolidWorks motion. They talk to each other. Okay, now the SolidWorks motion pauses. Okay, and then the EMS does the compute, force, torque, etc. Okay, and then says, okay, SolidWorks motion. Here's my torque now at this time position. What is my next position? And so on and so forth. That's how it's coupled. Okay. Uh, is there any equation to find current braking find current braking force? I actually don't know. I don't think there is an equation. Yeah. Well, there's no equation as far as I know. I mean, we are simulation experts, to tell the truth. We are not designers of braking of eddy current braking system, but as far as you know, there is no equation. Okay. Yeah, I mean, all I said now, this is another question. Can we solve linear braking system? Yes, of course. Whatever I said about the rotational braking system, because that most of the cases, are rotational, right? Whether it's a car or a train or a truck, most of the cases it's rotational. But in principle is the same. If you have linear, it works exactly the same way. Okay. Yeah, so the question again about eddy current braking force, I don't know of any equation. Okay. Okay, so any other question? All right. Thank you again. Thank you for attending. And make sure to attend future webinars. We have almost weekly webinars. So stay tuned, visit our website often. And of course, we have application notes, we have uh, blogs, we have YouTube channel where you post videos, okay? And if you want a customized web demo, please contact us and we'll do a one-to-one web demo. Thank you again and have a nice day. Bye-bye.